February 22nd, 1943, near Sbeitla, Tunisia, North Africa. Panzer Abteilung 501 advanced through the dusty Tunisian plain, hunting American armor. The German tank crews had heard rumors about the new American tank, the M4 Sherman. Intelligence reports described it as well-armed, well-armored, and produced in staggering numbers. But the Afrika Korps veterans dismissed these claims. American tanks? The same nation that had sent the pathetic M3 Lee with its awkward sponson-mounted gun? The same country whose military hadn't fought a major war since 1865? How dangerous could their newest design possibly be? The engagement was brief. First Armored Division tanks withdrew under German pressure. Among the abandoned American vehicles sat an M4A1 Sherman, intact, functional, crew compartment, still warm. The tank bore a name painted in white letters across its hull, War Daddy 2. The German tank commander approached cautiously, expecting booby traps or demolition charges. Nothing. The Americans had simply fled, leaving their vehicle behind without destroying it. This was a gift beyond measure. Germany's intelligence services had been desperate to examine American armor in detail. Now they possessed a complete, undamaged example. The crew that captured War Daddy 2 faced an immediate logistical challenge. How does one move a 30-ton American tank 350 kilometers across North Africa to Tunis? The journey took 4.5 days. German mechanics kept the Sherman running, impressed despite themselves by how easily the engine started, how smoothly the transmission shifted, how reliable the entire powertrain proved even under desert conditions. This was not what they expected from American engineering. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. At Tunis, War Daddy 2 was loaded aboard a transport ship bound for Germany. The voyage across the Mediterranean, through neutral waters, around occupied Europe, finally delivered the captured Sherman to the Army Weapons Office. From there, it travelled to Kummersdorf, the Wehrmacht's primary proving ground located 25 kilometres south of Berlin. Kummersdorf had served as Germany's weapons testing centre since 1875. Here, every new German tank underwent evaluation. Here, engineers tested prototypes, measured performance, identified weaknesses. And here, captured enemy equipment received exhaustive examination to assess capabilities and identify tactical countermeasures. War Daddy 2 arrived at Kummersdorf in April 1943. The German engineers and intelligence officers assigned to evaluate it had prepared for months. They had compiled every scrap of intelligence about American tank production. They knew the Sherman mounted a 75mm gun. They knew it weighed approximately 30 tons. They knew American factories were producing them by the thousands. What they didn't know was whether American engineering could actually produce a quality combat vehicle at such industrial scale. German tank production emphasized craftsmanship, precision manufacturing, and sophisticated engineering. Each German tank represented hundreds of hours of skilled labor. Could American mass production possibly match German quality? The testing program began with basic documentation. German engineers photographed War Daddy 2 from every angle. They measured armor thickness at every point on the hull and turret. They stenciled these measurements directly onto the tank's armor plates, noting thickness in millimeters and angles in degrees. Frontal hull armor measured 51 millimeters at 47 degrees from vertical. Turret front armor measured 76 millimeters. Side hull armor was 38 millimeters. These measurements revealed a tank with respectable but not exceptional armor protection. The sloped frontal armor was well designed, increasing effective thickness against projectiles. But the actual armor values were inferior to German medium tanks like the Panzer IV Ausf H. Next came examination of the main armament. The 75mm M3 gun mounted in War Daddy 2 was a medium-velocity weapon optimized for general-purpose combat. German engineers test-fired the weapon at Kummersdorf's ranges. The gun demonstrated good accuracy and acceptable penetration against moderate armour. Against heavy armour, it would struggle. The German 7.5 cm KUK 40L-43 gun, mounted on Panzer IV tanks, was superior in muzzle velocity and armour penetration. So far, the Sherman appeared to be exactly what German intelligence had predicted: a competent but unremarkable medium tank, produced in large quantities to compensate for mediocre individual performance. Then the engineers began examining the Sherman's automotive systems. And everything changed. The engine compartment revealed a Wright Continental R975C1 radial engine. This was an air-cooled, 9-cylinder radial aircraft engine adapted for tank use. It produced 400 horsepower, adequate for the Sherman's 30-ton weight. But the engine's installation, accessibility, and design left the German engineers stunned. Every major component could be accessed easily. The air filter could be removed and cleaned in minutes. The spark plugs were positioned for simple replacement. The entire engine could be removed from the tank in less than 2 hours, using standard lifting equipment. German tank engines required days of work to remove, often involving cutting through hull plates or removing major structural components. The transmission proved equally remarkable. The Sherman used a synchromesh transmission with 5 forward gears and 1 reverse gear. Shifting was smooth and required minimal effort from the driver. The clutch was hydraulically assisted, reducing driver fatigue. The entire drivetrain from engine to final drive incorporated modern automotive engineering principles. German engineers tested the transmission by driving War Daddy 2 repeatedly around Kummersdorf's test tracks. The tank shifted smoothly through all gears. The clutch engaged positively without slipping. The transmission operated quietly, without grinding or excessive noise. This was automotive engineering at a level German tank designers had not achieved. The suspension system drew particular attention. The Sherman used vertical volute spring suspension, a simple and robust design. Each road wheel was independently suspended on a vertical volute spring. The system was not sophisticated. It did not provide the smoothest ride, but it was incredibly durable and easy to maintain. A damaged road wheel could be replaced in the field using basic tools and a jack. The suspension components were standardized, meaning any replacement part would fit. German tank suspensions, particularly the complex interleaved road wheel designs on Panthers and Tigers, required specialized tools and extensive labor to repair. In winter conditions, mud and snow froze between the overlapping wheels, immobilizing the entire tank until crews could thaw and clear the ice. The Sherman's simpler suspension never experienced this problem. The crew compartment revealed another surprise. The Sherman's interior was spacious, well laid out, and logically organized. The driver's position featured clear instrumentation with gauges for oil pressure, coolant temperature, fuel level, and battery charge. The instruments were positioned where the driver could see them easily. The controls fell naturally to hand. Visibility through the driver's periscope was excellent. The fighting compartment provided adequate space for the 3-man turret crew. The commander's cupola offered good all-around visibility. The gunner's position featured a periscope sight and a telescopic sight, both of good optical quality. The loader had sufficient room to handle ammunition efficiently. German engineers noted that the Sherman's crew compartment was significantly more comfortable than comparable German tanks. The Panzer IV, Germany's standard medium tank, cramped its crew into a smaller fighting space. The Panther, despite its superior firepower and armour, featured a turret so cramped that loading the main gun required significant physical effort. The Sherman's designers had prioritized crew efficiency and combat effectiveness by providing adequate working space. This was not a detail that appeared in technical specifications or intelligence reports, but it was a factor that would significantly affect crew performance during extended combat operations. The most shocking discovery came when German engineers began extended mobility trials. They drove War Daddy 2 for hundreds of kilometers across Kummersdorf's varied test terrain. The Sherman performed consistently, reliably, without significant mechanical problems. The engine ran smoothly hour after hour. The transmission shifted cleanly through thousands of gear changes. The suspension absorbed punishment without failure. The tracks, while narrower than German tracks, proved durable and long-lasting. After 2 weeks of intensive testing that would have destroyed most German prototypes, War Daddy 2 remained fully operational and required only routine maintenance. German engineers compiled their findings into detailed technical reports. These reports were classified and distributed to Army Ordnance, tank design bureaus, and senior military leadership. The tone of these reports was professional, factual, and deeply concerned. The Sherman was not the crude, mass-produced weapon German propaganda had described. It was a sophisticated combat vehicle designed with completely different priorities than German tanks. Where German designers pursued maximum firepower and armor protection, American designers had prioritized reliability, ease of production, and logistical sustainability. The German reports acknowledged that in a direct combat engagement between a Sherman and a Panther, the Panther would win decisively. But the reports also noted that the Panther required 10 times the maintenance labor, consumed fuel at twice the rate, and broke down far more frequently. If Germany faced 100 Panthers or 500 Shermans, which represented the greater threat? The answer to that question became increasingly uncomfortable as the war progressed. By mid-1943, American factories were producing Sherman tanks at a rate of over 2,000 per month. German industry, even at peak production, never exceeded 400 tanks of all types per month. The industrial mathematics were devastating. For every German tank produced, America built 5 Shermans. For every hour of German tank maintenance required, the Sherman needed perhaps 15 minutes. For every litre of fuel a German tank consumed, the Sherman used half as much. These were not factors that appeared in dramatic tank versus tank combat, but they were the factors that determined who would win a multi-year industrial war across 3 continents. Albert Speer, Reich Minister of Armaments and War Production, visited Kummersdorf personally to inspect War Daddy 2. Photographs from this visit show Speer sitting in the commander's cupola, examining the interior, discussing the tank with engineers. Speer understood industrial production better than most Nazi officials. He had reorganized German war production, dramatically increasing output of tanks, aircraft, and ammunition. But even Speer's considerable skills could not change fundamental realities. Germany lacked the raw materials, the industrial capacity, and the labor force to match American production. Examining the Sherman made this reality tangible and immediate. This was not theoretical industrial capacity shown in statistical reports. This was a physical example of what American mass production could build. And if America could build tanks of this quality at this scale, what did that mean for Germany's chances of winning the war? The uncomfortable truth was that German engineers could not replicate American success, even if they tried. German industry operated under completely different constraints. Skilled labor was scarce and becoming scarcer as casualties mounted. Raw materials were limited by Allied bombing and the British naval blockade. Factories were dispersed to protect against air attack, complicating logistics and coordination. Quality control suffered as inexperienced workers replaced skilled craftsmen sent to the front. Under these conditions, German industry focused on producing smaller numbers of more powerful individual weapons. This strategy made sense given the constraints, but it meant that German tanks, while superior in direct combat, could never be produced in sufficient numbers to match Allied production. The Sherman's design philosophy represented the opposite approach. American designers accepted that their tank would be inferior in armor and firepower to the best German tanks, but they ensured it could be manufactured by the tens of thousands, maintained with minimal training, and kept operational under harsh field conditions. The Sherman used commercial automotive components wherever possible. The engine was a modified aircraft engine, proven and reliable. The transmission was based on civilian truck designs. The suspension was simple and robust. Every decision prioritized manufacturability and maintainability over raw combat performance. This was engineering for industrial warfare, not for individual duels. German tankers captured on various fronts confirmed what the engineers discovered at Kummersdorf. Interrogation reports from German prisoners who had faced Shermans in combat consistently mentioned American tanks that kept fighting despite multiple hits. German crews described Shermans that withdrew after battle, received rapid repairs, and returned to combat days later. They reported American armored units that maintained high operational readiness rates even after weeks of continuous combat. These observations contradicted German expectations. German propaganda portrayed American equipment as inferior, mass-produced garbage that would collapse under the strain of real combat. The reality was different. American equipment was designed to survive the strain of real combat. It was designed to be repaired quickly and returned to service. It was designed for a long war of industrial attrition. The testing of War Daddy 2 also revealed American attention to crew safety and survivability. The Sherman featured wet ammunition stowage, where main gun rounds were stored in racks surrounded by water glycol mixture. If the tank was hit and ammunition was struck, the liquid would help prevent catastrophic explosion. German tanks stored ammunition dry, making them more vulnerable to catastrophic fires if penetrated. The Sherman's crew escape hatches were well designed and easy to operate, allowing rapid evacuation if the tank was disabled. The fighting compartment included a fire extinguisher system that could be activated from multiple positions. These were not features that increased combat effectiveness directly, but they increased crew survival rates, which meant experienced tank crews could fight again after losing their vehicle. German interrogators questioning captured American tank crews noted another significant difference. American tankers received extensive training before deployment. They trained on the same tank models they would use in combat. They practiced crew coordination, maintenance procedures, and tactical doctrine. By contrast, German tank crew training had deteriorated significantly by 1943. New crews received minimal training on their vehicles, sometimes as little as 2 weeks, before being sent to frontline units. Replacement crews often had never driven or fired the specific tank model they would operate in combat. This training deficit, combined with mechanical unreliability, meant that even superior German tanks were often less effective than their specifications suggested. The implications of Kummersdorf's findings spread beyond tank design. If American industry could produce high-quality tanks at such scale, what did that mean for aircraft production? For naval construction? For artillery manufacture? Intelligence reports from other fronts confirmed the pattern. American B-17 heavy bombers were sophisticated aircraft produced by the thousands. American destroyers and escort carriers were being launched at rates that exceeded German submarine construction. American artillery, trucks, and small arms all showed the same characteristics. Adequate or good individual performance, combined with overwhelming quantitative superiority. Germany was fighting an enemy whose industrial capacity exceeded German capabilities by an order of magnitude. The German response to this realization was to double down on quality over quantity. If Germany could not match American numbers, perhaps Germany could produce weapons so superior that numerical inferiority became irrelevant. This thinking led directly to the development of the Panther and Tiger tanks. The Panther was designed specifically to counter Soviet T-34 tanks, incorporating sloped armor and a powerful long-barreled 75mm gun. The Tiger was designed as a breakthrough weapon, mounting an 88mm gun and thick armor that made it nearly invulnerable frontally. Both tanks were formidable combat vehicles that dominated any battlefield engagement when they functioned properly. But both tanks inherited the same weaknesses that Kummersdorf engineers had noted as American strengths: Panthers and Ind. Tigers were complex, difficult to produce, maintenance-intensive, and mechanically unreliable. The Panther's transmission was fundamentally the same design used in the lighter Panzer IV, leading to chronic failure when stressed by the Panther's 45-ton weight. The Tiger's Maybach engine was barely adequate for the tank's 56-ton weight, resulting in frequent overheating and mechanical breakdown. Both tanks required specialized recovery vehicles to tow them when disabled. Both consumed fuel at rates that strained German logistics. Both required extensive maintenance by skilled technicians. These were not minor inconveniences. These were fundamental design flaws that made Germany's best tanks strategically unsustainable. The contrast with American design philosophy could not be more stark. Where German engineers pursued perfection in individual vehicles, American engineers pursued adequacy in mass production. Where German tanks required extensive maintenance, American tanks required minimal service. Where German production emphasized craftsmanship, American production emphasized standardization. Where German logistics struggled to support complex equipment, American logistics was designed to support massive armies across global distances. The Sherman was not a perfect tank, but it was the right tank for industrial warfare, and that made all the difference. By late 1943, more captured Sherman tanks arrived at Kummersdorf for testing. Some were captured from British forces in Italy. Others came from Soviet units on the Eastern Front, where America supplied thousands of Sherman tanks under Lend-Lease. Each captured example underwent similar testing. Each example demonstrated similar characteristics: reliable, maintainable, well-designed for mass production. The consistency was remarkable. American quality control ensured that Sherman tanks produced by different manufacturers in different factories met the same specifications, performed to the same standards. German quality control, especially as the war continued, became increasingly erratic. Panthers produced in early 1944 had significantly better build quality than Panthers produced in late 1944, as experienced workers were conscripted and replaced with forced laborers and concentration camp prisoners. The captured Shermans at Kummersdorf also revealed American innovation in specific subsystems. The gun stabilization system drew particular German attention. The Sherman's 75mm gun was stabilized in the vertical plane, meaning the gun automatically compensated for vehicle movement while driving. This allowed American crews to fire accurately while moving, a capability German tanks completely lacked. German tankers had to stop their vehicles to fire accurately. This gave American crews a significant tactical advantage in mobile combat. They could advance while engaging targets. German tanks had to halt, fire, and then move. The time difference was measured in seconds, but those seconds could determine who shot first and who survived the engagement. The electrical system on captured Shermans impressed German engineers. The Sherman used a 24-volt electrical system with substantial generating capacity. This powered radios, gun stabilization, turret traverse motors, and other electrical equipment reliably. German tanks used 12-volt systems with marginal generating capacity, leading to chronic electrical problems. Sherman batteries were easy to access and replace. German batteries often required disassembling major components to reach. The Sherman's wiring harness was logically organized, with clear color coding and easy-to-follow routing. German wiring was complex, poorly documented, and difficult to troubleshoot. These details seem trivial compared to armor thickness and gun caliber. But reliable electrical systems meant reliable radios. Reliable radios meant better command and control. Better command and control meant more effective tactical coordination. Small advantages in engineering translated to significant advantages in combat effectiveness. The radio equipment in captured Shermans revealed another American advantage. The Sherman carried 2 radios as standard equipment. One radio operated on command frequencies for communication between tank commanders and higher headquarters. The second radio operated on unit frequencies for communication between tanks in the same formation. This allowed simultaneous command and tactical communication. German tanks typically carried one radio, forcing commanders to choose between listening to orders from above or coordinating with adjacent tanks. The American system was more flexible and more effective. It enabled the kind of fluid, coordinated armoured warfare that German doctrine emphasised, but German equipment struggled to support. American production methods were analysed based on examination of captured tanks. German engineers noted that Sherman hulls showed evidence of welding rather than bolting or riveting. Welded construction was faster and produced stronger joints. But welding required skilled labour and careful quality control. That American factories could produce welded hulls by the thousands indicated both substantial skilled labour forces and effective quality control systems. German factories struggled to maintain welding quality as the war progressed. The Sherman's cast turret was another production innovation. Cast armour was faster to produce than rolled and shaped armour plate. It allowed complex shapes that would be difficult to fabricate from flat plate. American foundries produced cast turrets efficiently while maintaining good metallurgical properties. German attempts to use cast armour often resulted in inferior metal quality with internal flaws and inconsistent hardness. The standardization of Sherman production was perhaps the most impressive aspect American industry demonstrated. Shermans were produced by multiple manufacturers. Chrysler, Ford, Fisher Body, Federal Machine and Welder, Pacific Car and Foundry, Baldwin Locomotive Works, American Locomotive Company, and Pressed Steel Car Company all built Sherman tanks. Yet parts were interchangeable between tanks produced by different manufacturers. A transmission from a Chrysler-built Sherman could be installed in a Ford-built Sherman. This required extraordinary coordination between manufacturers, strict adherence to specifications, and effective oversight. German tank production never achieved this level of standardization. Parts were often not interchangeable, even between tanks of the same model produced by the same factory at different times. The Sherman's track design represented another lesson in practical engineering. American tracks used rubber-bushed steel pins connecting the track links. This design reduced wear, decreased noise, and provided reasonable durability. German track designs varied by tank model, but all suffered from common problems. Steel tracks without rubber bushings wore quickly on paved roads. Rubber-saving track designs introduced during wartime deteriorated rapidly. Track pin replacement on German tanks required specialized tools and significant effort. Sherman track pins could be replaced with basic hand tools and a sledgehammer. A Sherman crew could replace a damaged track section in under an hour. A Panther crew might require half a day for the same repair, assuming they had the right tools and replacement sections available. The fuel system on captured Shermans revealed American attention to fire safety. The Sherman's fuel tanks were located low in the hull, away from the crew compartment, and separated by armoured bulkheads. Fuel lines were steel tubing rather than rubber hoses, reducing fire risk from combat damage. The engine compartment featured automatic fire suppression that activated if temperatures exceeded safe limits. German tanks placed fuel tanks wherever space permitted, often adjacent to crew positions. Fuel lines were frequently rubber hoses vulnerable to damage. Engine compartment fires were common and often catastrophic. The Sherman's design minimized fire risk through careful engineering. German designs accepted fire risk as unavoidable in combat vehicles. By mid-1944, German forces had encountered improved Sherman variants. The M4A3E8, designated the Easy 8 by American crews, began appearing in Europe in December 1944 during the Battle of the Bulge. This variant featured the horizontal volute spring suspension system with wider tracks, improving flotation and cross-country mobility. It mounted the 76mm M1A2 gun, providing significantly better armour penetration than the original 75mm weapon. The Easy 8 represented iterative improvement on proven design. American engineers had identified the Sherman's weaknesses and addressed them without completely redesigning the tank. This was exactly the kind of continuous improvement that German industry struggled to implement. German intelligence reports from Normandy in summer 1944 painted an increasingly grim picture. American armoured units were maintaining operational readiness rates above 70%, even during intensive combat operations. German armoured units were struggling to maintain 50% readiness. The difference was not combat losses. The difference was mechanical reliability. American tanks kept running. German tanks kept breaking down. Panther transmissions failed after 50 to 100 kilometers. Tiger final drives stripped their gears under combat stress. German recovery vehicles broke down, trying to tow disabled German tanks. Meanwhile, American tank crews performed field repairs and returned to combat. The Battle of Aracourt in September 1944 provided a clear example of how American engineering advantages translated to battlefield success. The German 5th Panzer Army attacked American positions near Aracourt, France with approximately 280 Panthers and 113 Panzer IV tanks. The defending American forces had primarily Sherman tanks from 4th Armoured Division and 6th Armoured Division. On paper, the Germans had overwhelming superiority. Panthers completely outclassed Shermans in armour and firepower. German numerical advantage was substantial. German tactical doctrine emphasized concentrated armoured assault. Everything favoured German victory. The battle lasted from September 18th to September 29th, 1944. American forces destroyed or disabled approximately 286 German tanks for loss of approximately 48 American tanks. This was not a close engagement. This was a decisive American victory against theoretically superior German armour. How did this happen? German. After-action reports and interrogation of captured German tank commanders revealed the answer. Mechanical failures immobilized German tanks before they reached combat positions. Panthers broke down during approach marches. Recovery vehicles could not retrieve all disabled tanks before American forces advanced. German units that did reach combat positions found themselves outnumbered because so many of their tanks had broken down en route. American forces, by contrast, maintained high operational readiness throughout the battle. Damaged Shermans were recovered, repaired, and returned to combat within days or even hours. American maintenance units worked efficiently with adequate spare parts and proper tools. American crews could perform many repairs themselves without specialized technical support. The cumulative effect of these small advantages produced overwhelming tactical superiority. German commanders planned operations assuming their tanks would reach the battlefield. American commanders planned operations knowing their tanks would reach the battlefield. That difference in confidence, based on proven mechanical reliability, fundamentally altered how each side conducted armoured warfare. German tank designers were aware of these problems. Engineers at Henschel, Daimler-Benz, and MAN, who designed German tanks, understood that reliability mattered. They knew that complex designs caused maintenance problems. They knew that undertested prototypes would fail in service, but they operated under impossible constraints. Hitler personally intervened in tank design, demanding specific capabilities regardless of engineering feasibility. Production schedules were compressed to rush new designs into service before adequate testing. The demands of total war meant that long-term reliability received lower priority than immediate combat capability. American designers faced no such pressures. They had time to test thoroughly, refine designs, and solve problems before mass production began. The Panther tank exemplified these German design problems. The Panther was conceived in 1941 as a response to the Soviet T-34. German engineers studied captured T-34s and incorporated the best features. Sloped armour, wide tracks, powerful gun. The prototype Panther was tested at Kummersdorf in September 1942 and accepted for production. Production began in December 1942. The first Panthers were sent to the Eastern Front in summer 1943 for the Battle of Kursk. Of the approximately 200 Panthers deployed, nearly all broke down before or during the battle. Transmission failures, engine fires, final drive failures. The Panther was a sophisticated design rushed into production before it was ready. The result was a weapon that looked impressive on paper, but couldn't be relied upon in combat. If you find this story engaging, Please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. German attempts to improve Panther reliability continued throughout the war. Engineers strengthened the transmission. They improved the engine cooling system. They reinforced the final drives. Each improvement helped, but never solved the fundamental problem. The Panther was too heavy for its drivetrain. The engine was barely adequate. The transmission was overstressed. No amount of incremental improvement could fix design decisions made at the beginning when performance was prioritized over reliability. By contrast, the Sherman's design had been conservative from the start. The engine had adequate power reserves. The transmission was not overstressed. The suspension could handle the weight. This conservative design approach meant the Sherman could be improved incrementally without fundamental redesign. American industry's ability to produce spare parts at scale gave American forces another critical advantage. When a Sherman broke down, replacement parts were available. Supply chains delivered engines, transmissions, tracks, and components to forward maintenance units. German supply chains struggled to deliver fuel and ammunition, let alone spare parts for complex tank systems. A disabled Panther often remained disabled because replacement transmissions were not available. A disabled Sherman was typically repaired and returned to service because replacement parts were in stock. This difference in logistics support meant that American armored units grew stronger over time, while German armored units grew weaker. The Ardennes Offensive in December 1944, known to Americans as the Battle of the Bulge, demonstrated how German engineering sophistication could not overcome logistical constraints. Germany committed its last strategic reserves to this offensive, including several panzer divisions with Panthers and Tiger IIs. The plan required rapid advance to seize American fuel dumps because German logistics could not supply sufficient fuel for extended operations. From the beginning, mechanical problems plagued German armor. Panthers broke down during the approach march. Tiger IIs exceeded weight limits for bridges, forcing them onto limited routes. Fuel consumption exceeded projections. Within days, German armored spearheads were immobilized not from combat losses, but from empty fuel tanks and mechanical breakdown. American defenders at Bastogne included elements of 4th Armored Division with Sherman tanks, including some of the new Easy 8 variants. These Shermans operated continuously throughout the battle, maintaining combat effectiveness despite severe winter weather. American maintenance crews worked in sub-freezing temperatures to keep tanks running. German maintenance crews worked in the same conditions but faced far more severe mechanical problems. Frozen mud between Panther road wheels immobilized entire tanks. Engine compartment fires destroyed Panthers when crews attempted cold starts. Tigers sat abandoned when their crews could not repair complex mechanical failures under field conditions. The contrast in winter reliability was stark and documented in captured German records. German unit war diaries from the Ardennes offensive recorded daily operational readiness rates. Some Panther battalions reported less than 30% operational readiness by late December. American unit records showed Sherman battalions maintaining 60 to 70% readiness under identical weather conditions. The difference was not maintenance effort. German crews worked desperately to keep their tanks running. The difference was fundamental design. Shermans were designed to function under harsh conditions with minimal maintenance. Panthers required extensive maintenance even under ideal conditions and became nearly impossible to maintain in severe weather. After the war, Allied forces conducted extensive interrogations of captured German tank designers and engineers. These interrogations, preserved in the National Archives, revealed German engineers' perspectives on their own designs versus American designs. Heinrich Ernst Kniepkamp, a senior designer at the Weapons Office, testified that German tank design emphasized combat performance above all other considerations. Reliability, maintainability, and production efficiency were secondary concerns. When interrogators asked why German designers did not prioritize reliability like American designers, Kniepkamp replied that German military leadership viewed reliability as the responsibility of maintenance units, not designers. If tanks broke down, maintenance units should repair them. This attitude persisted, even as evidence mounted that German maintenance units could not keep pace with mechanical failures. Ferdinand Porsche, whose designs competed for the Tiger contract, provided different testimony. Porsche argued that German industry lacked the precision manufacturing capability to produce truly reliable complex systems at scale. American industry had decades of automobile production experience, generating expertise in mass-producing reliable mechanical systems. German industry had less automotive experience and relied more on craftsmanship than systematized production. Porsche noted that captured American tanks showed evidence of precision manufacturing that German factories struggled to match. Tolerances were tighter. Quality control was more consistent. These small differences accumulated into significant reliability advantages. Albert Speer's interrogations focused on industrial capacity and production philosophy. Speer acknowledged that German tank production never achieved American scale, despite his extensive efforts to increase output. He identified several limiting factors. Raw material shortages constrained production volume. Allied bombing disrupted supply chains and destroyed factory capacity. Labor shortages forced the use of forced laborers and prisoners who lacked training and motivation. But Speer also noted that German tank designs were inherently more difficult to produce than American designs. The Sherman used simpler manufacturing processes, required less specialized tooling, and accommodated less skilled labor. German tanks required specialized equipment, skilled workers, and precision machining. In an industrial war, the Sherman's design philosophy was superior not because it produced better individual tanks, but because it produced adequate tanks in overwhelming numbers. Kummersdorf continued testing captured American equipment throughout the war. Sherman variants, tank destroyers, armored cars, and half-tracks all underwent evaluation. A consistent pattern emerged. American equipment was not technically superior to German equivalents, but American equipment was more reliable, easier to maintain, better suited for mass production, and designed with logistical sustainability in mind. These were not dramatic differences. No single American design feature was revolutionary, but the cumulative effect of dozens of small advantages in engineering, production, and logistics created overwhelming superiority at the operational level. German tankers captured in the war's final months consistently reported that they feared American numbers more than American tank quality. One Panther commander captured in April 1945 testified that he knew his Panther could destroy any Sherman it encountered, but he also knew that he would face 5 or 10 Shermans for every Panther. He knew his Panther might break down before reaching combat. He knew spare parts might not be available if repairs were needed. He knew American tanks would keep coming regardless of how many were destroyed. This psychological weight of American industrial superiority was as devastating as the physical reality. German tankers fought not just against American tanks but against American industry, and America's industry was an enemy that could not be defeated by superior tactics or better training. The final German assessment of American tank design came in March 1945 from the Weapons Office's summary report on captured Allied equipment. This classified document synthesized findings from 4 years of testing captured tanks. The report concluded that the Sherman was the most successful tank design of World War II, not because of technical superiority, but because of its optimization for industrial warfare. The report noted that German tanks achieved superior performance in individual combat engagements, but the report acknowledged that individual combat performance was not the determining factor in armored warfare. Operational readiness, logistical sustainability, and numerical superiority determined outcomes. By these measures, the Sherman was decisively superior to all German tanks. The report made specific recommendations for future German tank design. Prioritize reliability over maximum performance. Simplify designs to improve manufacturability. standardize components across models to improve logistics, reduce maintenance requirements to levels achievable by unit maintenance personnel, design for repair and replacement rather than expecting perfection. These recommendations essentially described American design philosophy. But by March 1945, Germany had no capacity to implement these recommendations. The war was weeks from ending. German industry was collapsing. No new tank designs would be produced. The lessons learned from testing captured Shermans would never be applied to improve German tanks. War Daddy 2, the M4A1 Sherman captured in Tunisia in February 1943, remained at Kummersdorf until the facility was overrun by Soviet forces in April 1945. Soviet troops found extensive documentation of German testing programs, including detailed reports on American equipment. These reports were shipped to the Soviet Union and studied by Soviet tank designers. The reports influenced Soviet thinking about tank design in the immediate post-war period. Soviet designers noted the same lessons German engineers had learned. Reliability mattered. Maintainability mattered. Industrial producibility mattered. The T-54 tank, which became the Soviet Union's standard medium tank after World War II, incorporated many of these lessons. American occupation forces discovered additional German testing reports at other facilities. Reports from testing facilities at Birka and elsewhere confirmed Kummersdorf's findings. All reports showed consistent German conclusions about American equipment: well designed for production, reliable, maintainable, not technically superior but operationally dominant. These reports were classified and stored in American archives. Decades later, when these documents were declassified, historians gained detailed insight into how German engineers viewed their own equipment versus Allied equipment. The picture that emerged contradicted post-war narratives about German technical superiority. German engineers themselves acknowledged that American engineering philosophy was superior for the kind of war actually being fought. The lessons from testing captured Shermans influenced American tank design for decades after World War II. The M48 Patton tank developed in the 1950s continued Sherman design philosophy: reliable, maintainable, suitable for mass production. The M60 tank that replaced the M48 maintained these priorities. The M1 Abrams tank, developed in the 1970s, incorporated advanced technology, but never abandoned the fundamental principle that reliability and maintainability were as important as combat performance. American tank designers had learned during World War II that wars are won by tanks that reach the battlefield and keep fighting, not by tanks with impressive specifications that break down before engaging the enemy. German tank design after World War II took a different path. West Germany's first post-war tank, the Leopard 1, emphasized mobility and firepower over armor protection. But Leopard designers prioritized reliability and maintainability from the beginning. The Leopard used a proven commercial diesel engine. The transmission was robust and well tested. The suspension was simple and durable. These design choices reflected lessons learned during World War II. German designers had finally accepted that engineering sophistication must be balanced with reliability and ease of maintenance. The Leopard 1 was successful precisely because it abandoned the Panther's philosophy of maximum performance regardless of reliability. The story of War Daddy 2 and the German testing program at Kummersdorf reveals a fundamental truth about armored warfare. Technical sophistication does not guarantee victory. The most powerful gun means nothing if the tank breaks, down en route to battle. The thickest armor provides no protection if the tank sits disabled awaiting spare parts that never arrive. The most advanced engineering is worthless if it cannot be produced in adequate numbers to influence battlefield outcomes. The Sherman won not because it was the best tank. The Sherman won because it was the right tank for industrial warfare. German engineers understood this by 1943 when they first tested War Daddy 2. They measured its armor and found it adequate but not exceptional. They tested its gun and found it effective but not outstanding. They drove it extensively and found it reliable, maintainable, and well suited for mass production. They compared it to German tanks and concluded that American engineering philosophy was superior for the war being fought. But understanding the problem did not enable Germany to solve it. German industry could not replicate American production scale. German designers could not abandon their emphasis on maximum performance. German logistics could not support mechanically complex tanks across extended campaigns. Germany was locked into a strategic approach that could not succeed against American industrial power. The American soldiers who crewed Sherman tanks rarely knew about German testing programs. They did not know that German engineers had studied captured Shermans and reached conclusions favorable to American design. What American tankers knew was that their Shermans kept running. They started reliably. They shifted smoothly. They could be repaired quickly when damaged. They did not leave crews stranded behind enemy lines with mechanical failures. These practical advantages mattered more than any technical specification. A Sherman crew could focus on fighting the enemy rather than fighting their own equipment. That psychological confidence, backed by genuine mechanical reliability, made Sherman crews more effective in combat. The final chapter in War Daddy II's story came in April 1945 when Soviet forces overran Kummersdorf. Soviet troops found several captured Allied tanks at the facility, including at least one Sherman. Whether this was War Daddy II specifically cannot be confirmed, but the timing and location make it likely. Soviet forces examined these tanks with interest, noted the German test reports, and shipped selected examples back to the Soviet Union for further study. The Sherman's journey had taken it from American production lines to North African battlefields to German testing facilities to Soviet hands. 4 nations had now studied this tank, each drawing their own conclusions about what made it effective or ineffective. For historians studying World War II armoured warfare, the German testing program provides invaluable perspective. It reveals what German engineers thought about their own tanks versus enemy tanks. It shows that German engineers were not blind to their design's weaknesses. They understood reliability problems. They recognized production difficulties. They knew their tanks could not be sustained in extended operations. But understanding these problems did not enable solutions. Institutional momentum, political pressure, resource constraints, and the demands of total war locked Germany into producing tanks that were technically impressive but strategically unsustainable. The Sherman's success demonstrated that war is not decided by which side has the best weapons. War is decided by which side can produce adequate weapons in overwhelming quantities, sustain them logistically, maintain them effectively, and employ them continuously. American industry mastered all these requirements. German industry excelled at producing sophisticated individual weapons, but failed at the systematic requirements of industrial warfare. The Sherman embodied American industrial power. The Panther embodied German engineering ambition. In the contest between mass production and craftsmanship, mass production won decisively. Modern military forces continue learning from World War II lessons. Military procurement today emphasizes reliability, maintainability, and sustainability alongside combat performance. The most advanced weapons are useless if they cannot be maintained by unit-level personnel with standard tools. The most powerful systems are strategic liabilities if they require extensive supply chains vulnerable to enemy interdiction. The lessons German engineers learned from testing War Daddy II in 1943 remain relevant in 21st century military planning. Operational effectiveness depends on more than technical specifications. It depends on the entire system of production, logistics, maintenance, and sustainment that supports frontline equipment. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.